This is example 7 on page 91 that we're looking at. Okay, and in this example, we are going to discuss the convergence of the series sum 1 over 2 at 2 to the n minus 1. And what this is going to lead us to is a new convergence test for series that's going to be particularly useful. Okay, so as we look at this example, we start by making an observation. Okay, 1 over 2 to the n minus 1. If you look at the denominator, we've got a 2 to the n and a minus 1. And if you think about those two terms, ask yourself, which term is the significant one? Okay, you can convince yourself that it must be the 2 to the n because that's growing really, really fast. Subtracting 1 has almost no effect on that series. Okay, so our kind of starting observation here is that this series that we're given is similar to the series that we would get if we just kind of ignored the minus 1. Okay, what does that series that we just kind of wrote down above look like if we write out the terms? Okay, well, let's do that. So first term would be 1 over 2, and then we'd get 1 over 2 squared, which is a fourth, and then 1 over 2 cubed, which is an eighth, and so on. And I'm curious if you recognize what kind of a series that is that we're looking at. You might remember back in the last section you talked about geometric series, and this is a geometric series because it has a common ratio of 1/2. Okay, 1/2 is the common ratio because of the fact that you can multiply every term in your series by 1/2 and get to the next term. Okay, is that a convergent geometric series? Well, if you think back to what we talked about in section 8.2, it is, because this common ratio is between -1 and 1. That's how we tell if a geometric series converges. Okay, so putting it all together, what we could say is the following. Okay, we know that 1 over 2 to the n converges because it's geometric, and the series that we started with is similar to that series. So a reasonable conjecture to make here is that even though the series we started with isn't exactly the same, it's probably going to behave the same way that the geometric series converges. Okay, so since one over 2 to the n is a convergent series, we conjecture, okay, and I emphasize this is just a guess. We don't know this for sure. We conjecture that the series that we were given also converges. Okay, and what we have just described is the basic logic that you use when you use what's known as the limit comparison test. Okay, so let's scroll up here. This is taking us to the next page. Okay, the limit comparison test is a way of determining whether a series converges by comparing it, essentially, to another series that we know something about. Okay, and here's how it starts. Suppose that we have two series, an and bn, okay, with positive terms. The way the limit comparison test works is that you start by taking a limit of bn over an, so the term in one of your series over the term in the other, and you're going to get a number when you take that limit that we're going to call c. And what we'd like is for that number c to have two properties. We would like it to be positive and finite. And it turns out that if it has both of those properties, the conclusion is that an and bn will either both converge or both diverge. In other words, they're going to behave in the same manner. Okay, now this convergence test is quite a bit more complicated than any that we've looked at so far. That's okay. Well, we're going to do some examples and we'll make sense out of this together. Let's make a couple of comments, though, before we do that. Okay, so the first note here. Okay, the general purpose of the limit comparison test is to choose, and I emphasize the word choose, a nice series an, okay, whose convergence or divergence is known, something that we can easily figure out, to decide whether or not the given series Bn converges. So the idea is, in the problem, you're going to be given this series Bn, okay, and you're going to choose a second series that's similar to it, okay, and kind of use what you know about An to decide what happens with Bn. Okay, so how do we choose the series An? Okay, well, let's think about what are the nicest types of series that we know about so far. Okay, there are really two types I can think of. Okay, geometric series. That's a nice series because we can just look at the common ratio and decide immediately whether it converges. There's one other type of series that's nice, and that's a p-series. You can look back a couple of pages and see the definition of a p-series. So generally, when we use this test, we're going to be starting with our series Bn. We're going to try to find a p-series or a geometric series An that's similar to it, and we're going to perform the test